So, typical electronic system, right? Modern system which you see and use nowadays basically has these major components. One is, of course, the computing, right? Where you do your processing. Essentially, there is a microprocessor. Then you have storage, which consists of memories, both on chip, off chip. Off chip memories would be non-volatile memories, like you get your USB stick, SD cards, etc. Hard disks. You have physical interfaces in your system, keyboards, displays, other sensors, and so on. And of course, most of these systems nowadays are connected, right? So there will be some communication, which will be a radio of some kind, perhaps, and maybe even wired interfaces for some kinds of systems. And of course, you have a power source out here. Now, the power source has all the electronic systems run off DC voltages. Though there are some special examples where you'll have AC type signals for doing computing, which we might get to, if time permits, towards the end of the course. So you have DC voltage source, and the source supplies some current I, and the current gets divided into all these different components. You have current for the computing labeled IP out here, current for storage labeled IS, current for the physical interfaces IU, and current for communication IX. All these currents are functions of time. They keep fluctuating with time. Right? And for example, if I'm not doing any communication, hopefully the IX will be almost close to 0. Whereas the voltage is supposed to be constant. Right? You want a constant voltage for your system, 3 volts, 1.5 volts, 1 volt, whatever the system is. Of course, in reality, the voltage will also change with time, but it's a very slow change. Because if you have a battery, for example, the battery voltage will keep on reducing as a function of time, and after some time, the voltage is so low that your system will not operate. So, some definitions of these quantities, power and energy. So, power, as we know, is essentially the product of voltage times the current. So, what voltage, what current? So, you take any element in the circuit, you look at the voltage drop across the element and the current going through the element. So, V times I is the power delivered into that element. If in the case of a battery, the current comes out of the positive terminal of the battery, so we have a negative sign. So, power is provided by the battery, whereas for all the other elements, the current enters through the positive side. Wherever the positive voltage drop is there, the current enters into that system from there. So, these consume energy, right? So, so power clearly is a function of time, because current is a function of time. So, you have what is essentially instantaneous power, V times I. And typically when we say, okay, this system consumes so much power, so many milliwatts, so many watts, we are talking of average power, right? And average power is you take the power measurement for some duration of time and then average it out. Okay, so essentially integrate power from 0 to t and divide by the time interval over which you have made the measurement. And the units of power is watts, right? Voltage times amperes is watts. And energy is basically the integral of power. The rate of consumption of energy is power, so the integral of power is energy. So if you want to measure the energy consumed in a particular duration, you measure the power, instantaneous power, and integrate it for that duration, and you get the energy consumed by the system for that duration. So these are all very basic definitions, but it's important to again make sure you don't you have these in mind, so that when you're doing your measurements or design and so on, so you know how to measure and what to measure. So what are some typical power numbers, right? What is the scale of these numbers? So nowadays you get, of course, our old we had 60 watts, 100 watts, filament based light bulbs, but now you can get much more efficient bulbs which have the same kind of brightness, right? LED based, you have CFL and so on. So you might get a bulb which consumes 10 watts of power. If you take our desktop computers, that could be about 50 watts. A laptop would be about maybe 20 watts. A mobile phone will be much lower power. And here I'm kind of showing 3 different numbers. And it is kind of true for some of the other smarter systems like computers and laptops, where the power consumption really depends on the state of the system, and there is smarts in the system to regulate the amount of power you consume, unlike in a typical LED or a lamp, right? So you can also think of how to make bulbs smarter, lamps smarter. Can you include something so that you can reduce the power consumption of a LED? But basically in the phone, for example, we have powers which could be 70 milliwatts during idle to 270 milliwatts to a watt when it's kind of operating, we are talking on the phone. You have something called a smart watch. Nowadays you might have seen advertisements by these various companies, Samsung, Apple, Pebble, etc. So there the power consumption is even lower. Here what I am saying, listing is average power consumption. Okay, so there it would be about, say, maybe 3 milliwatts of power. Now in comparison, humans, people have reported, you can look up literature, if you do Google search, you'll find various references. Based on the calorie consumption and average calorie consumption and so on, you can estimate the power consumption of a human being, which is about 100 watts. And within a human being, the most power consuming portion is the brain, which is about 20 watts of power. So this is just to give you a kind of a context and comparison, right? A laptop and a human being are computing, it's kind of almost the same amount of power we are consuming. When you're doing design, of course average power is important, but as a designer of the system, instantaneous power is also very important. You can have a lot of fluctuation between the average power and the instantaneous power. For example, in the case of the smartwatch, on an average it would just perhaps consume just 3 milliwatts of power, but whenever the smartwatch communicates with a cell phone, because that's what a smartwatch is supposed to do, it's supposed to be in contact with the cell phone, it will turn on the radio, right? And that time, for the duration the radio is on, the power consumption is much, much higher, right? An order of magnitude higher, maybe even more. In the case of a smartwatch, it could be about 60 milliwatts of power. So as you're designing this system, that is very important, because because the power supply which provides that power should be able to handle these bursts, right, which can be off, the average and the instantaneous could be off by orders of magnitude. So your power supply system should be able to supply these large variations. Now, why is the average so low and burst so high? Well, it's because you make sure you don't use these high power consuming entities as often, right? You use them very sparingly. That is called duty cycling. You keep them off most of the time. Only when you want to really use them, you turn them on. So this is one of the most, shall we say, effective ways of reducing power, is what is called duty cycling, right? It's very common sense, nothing, no rocket science, but it works. You keep things off and turn them on only when you need to. And the process of doing that, of automating that, how do you intelligently keep things on and off and so on, so that can become quite sophisticated. And so there could be a lot of interesting algorithms and so on, which might have to be developed to intelligently turn on things only when you're required to do so. Okay, so we have this system, and we said the battery delivers the power of V times I, and then each component of the system, the 4 major components, each of them consumes some power. What happens to that power, right? You are taking out power from the battery or the power supply, and you're putting it into these components. Finally, what happens? Yes, you're doing some work, computing work, information processing, something is happening. But, is that all? Well, the power gets transformed, right? You have electrical power that gets transformed to heat primarily. And that is true for most of the, for example, in computing you have processors, memories and so on, and you draw power and you do your processing, but then that power which you have drawn is lost as heat. When you have these physical interfaces, like for example a display and so on, there of course some of the power gets transformed into light, and light comes out, maybe sound if you're using audio. And then you have radiation, where when you're doing communication, you have a radio and you actually put power into the radio, which gets transmitted out. If you have an ultrasonic transducer, for example, you will put power into the transducer to send out ultrasonic energy. So primarily most of the power in systems goes off as heat. Okay. Really it depends on the system, but mostly it goes off as heat. So it's kind of useful to understand what is heat and what is the implication of heat for your system. So you take any particular component out here. Okay, this could be a processor chip, for example, and it has a certain voltage drop across it, and there is a certain current flow through it. So we know that you are putting in power V times I, right? And so what happens to that power? That electrical power is when it gets dissipated, right? Whenever the like the current goes through a resistor or any dissipative element, it gets converted to heat. So really you're generating heat energy. So that heat, what happens to that heat? Right? Some of it is used to heat up that entity, that device, and then some of it gets lost. Basically you will have a heat loss, or there is a rate at which heat gets lost. Essentially heat power, Q, gets lost due to three primary mechanisms. One is conduction. When the processor chip is mounted on a PCB, some heat gets conducted from the processor chip to the PCB, though the PCB is a poor conductor. Maybe you might have a heat sink and it might go to the heat sink through conduction. Then you have whenever you have fluids around the chip, for example air is the most common fluid used for cooling, convection happens, the fluid comes, takes out the heat and takes it away. And then you have radiation, right? Because always you have any body which has a non-zero temperature will radiate heat, right? And it will also absorb heat, depending on, always you're radiating energy. And so these three primary mechanisms cause the loss of power. You lose out power. And so whatever power is, so you put a power Vi out here into the system, and you lose power Q due to these various mechanisms: conduction, convection, radiation. So the remaining power, basically the difference, is used to heat up the body, and the amount of change of heat, the temperature, is related to the amount of heat you put in and the heat capacity of the body. Certain things have very large heat capacity, so you have to put in a lot of heat for you to make a small change in temperature. Whereas some things like metals and so on will have low heat capacity, small heat, temperature will go up. So the temperature will change. And you see, these are all functions of time dynamics basically. And if you have constant power being put in, constant power being lost due to radiation, eventually it will reach a steady state, and then the system will reach a certain temperature, there will be certain temperature in the ambient, and then everything will stabilize. So so power consumption is kind of really important from this point of view of temperature, because as temperature goes up, the reliability, every device has a certain sweet spot for operation of the temperature. For example, for us, as soon as it hits 40 degrees, things become really bad, right? Even 30 is kind of getting there, 40 is miserable, 50 you will probably not survive for too long. So it's kind of like that. So every system has a certain sweet spot of temperature, and so it's kind of important to make sure that you manage the thermal profile of your system, and you manage it by multiple ways. One is, of course, you make sure you dissipate less. That is where low power design comes in. V times I you try to reduce by reducing I and reducing V, right? In addition, you pay attention to Q, which is the heat loss, and you try to make that as efficient as possible. You are able to take out heat as quickly and as efficiently as possible. That is basically part of the heat transfer and thermal design and so on. So whenever we talk of low power, the primary driving force is essentially this, is to make sure that our system doesn't heat up too much. And but in addition to power, we are also interested in energy. And why is that? Because when our system is not connected to the wall, like if I were to remove the plug from the socket right now from a laptop, it has to run off the battery of the laptop. And the laptop will have, the battery will essentially has some amount of energy which is there, right? And usually these batteries, most of the batteries we use have energy in the form of chemical energy, right? So there are some chemical redox reactions which happen, which essentially allow you to extract the chemical energy to electrical energy. So here I've kind of listed out a few example batteries. For example, the smartwatch might use a battery which is a lithium polymer type battery, very thin flexible batteries, because these devices are very small. And this particular smartwatch I looked up had 3.7 volt voltage and about 130 milliamp hours. Typically the battery specs have this units of milliamp hours. Milliamp is current, hours is the unit of time, so the product is really charge. So many coulombs of charge is there, and when you multiply all these three together, you will basically get the charge times voltage is giving you the energy stored in the battery. Of course, you should realize that as you start drawing the charge from the battery, the voltage of the battery will also start coming down, and effective energy you can get might be less than just what you get by just multiplying these two numbers. But this is kind of a good first estimate to compare different batteries. So you have about 1732 joules of energy for a lithium polymer battery used in the smartwatch. For example, the smartwatch I mentioned, which runs for 7 days on this battery. Okay, so if instead I had this button cell CR2032, which is a popular coin cell, that has 3 volts and about 225 milliamp hours. So you multiply 3 times 225 times 1 hour, which is 3600 seconds, you get 2430 joules. So if I had taken my same smartwatch and instead of using the lithium polymer I put this, I would get about 30% more lifetime. Instead of 7 days, maybe I'll get it to run for 10 days without having to change the battery or charge the battery. Your cameras, NIMH, those cells which you use, they have a substantial amount of charge, because these cameras have all these shutters and all those mechanical things which needs more energy, and that has 12,000 joules, right? And finally, if you take a smartphone, the typical lithium ion battery there might have 20,000 joules. So of course you have all other kinds of battery with different capacity. You can make custom batteries and so on, and the energy, which is voltage times current times time, right? So that is basically tells me if I have a certain operation which takes some amount of energy, then for a given amount of battery there is only so many operations I can do. So if I want to maximize the lifetime of a battery, what I need to do is to reduce the energy per operation. So so what we have here is that if we reduce energy consumption, we will reduce power consumption, because rate of consuming energy is power. But reducing power doesn't necessarily reduce energy consumption, because when I say I'm reducing power, one way of reducing power could be just consuming energy at a slower pace, right? Power is rate of consumption of energy. If I consume energy at a slower pace, that means for the same amount of work I need to do, I'll just take longer time and eventually I'll consume the same amount of energy, right? So reducing power doesn't mean reducing energy, whereas the other way is true. Reducing energy does imply reducing power. And so if possible, we should try to reduce energy consumption, and having done that, if you are not meeting the power profile, then the only thing you have is to reduce the rate at which you are consuming energy by slowing down systems so that you reduce the power consumption. Now let's look at dive deep a little bit more into a kind of popular electronic system which all of you use, which is a smartphone. Okay, and kind of look at this system and see where all power goes. What are all the components, how much power they consume. Because at the end of the day, we are interested in reducing the power of systems, okay, not just individual components. So one needs to have a holistic view of what are all the components which are contributing to the power consumption. So we'll take a smartphone, and this is basically based on some work which was reported in Usenix in 2010 by Carol from Australia. And what they did was they took open source smartphone hardware platform, and they instrumented that platform to measure power of different components. Now if you take a smartphone, you have the processor out here, some kind of application processor, probably most likely it will be some ARM processor, and then you have various components around it. For example, you have the GSM modem, which allows you to talk to the wireless network and do your calls, etc. You have Wi-Fi, which allows you to connect to your LAN wirelessly. You have audio related amplifiers, video, some codecs and so on for speech. You have other wireless interface like Bluetooth, which connects to for short distance communication. GPS is there to help you to do locationing, and you have basically certain other components like long-term storage with SD card, some external memory, display, graphics controller, and on-chip non-volatile storage, and some on-chip memory. Right. So this particular system these people studied had all these components, which are kind of typical of most smartphones. So what they did was, this particular system had this system on chip, that is this application processor, which has an ARM processor and certain other components like memories, flash, etc. So that makes it a system on chip. Multiple pieces are put on the same chip, and it was a system on chip from Samsung. The CPU was ARM, running at 400 megahertz, some memory, 128 megabytes, 256 megabyte NAND, modems, etc., etc. Okay, and then they had this battery, which was lithium-ion battery. So nothing exceptional about this system, just a typical smartphone system. So how did they go about measuring the power consumption of these different components? Well, what do you have to do? You have to basically measure the current and measure the voltage, right? You have to measure the current going through that individual piece and measure the voltage across that piece. Now, if you recall that diagram I had shown earlier with all these pieces in parallel connected to the supply, voltage will be the same for all of them. So you measure the voltage at the source, that you get. And if you're lot of these experiments, you would probably want to use a controlled voltage supply. Otherwise, things become more complicated. You might have a power source, maybe a power supply in your lab, which you use, and then you set the voltage, and then hopefully the power supply can maintain that voltage for the range of currents which are taken by this. So voltage measurement is pretty easy. Current measurement is trickier, because to measure current you have to put an ammeter, right, in series. So how is that done? Well, one way it is done is to put what these guys did was put a very small resistance in series to that component. They call it a 0 ohm resistor, but it's not really 0 ohms, it will be a very small number, right? Maybe an ohm or something. You choose the resistance as that because there will be a series voltage drop across that resistance, because the current to that component is going through the resistance and then into that component. So that voltage drop you want to make sure is very small and doesn't perturb the operation of that component. So what they have chosen is something where the voltage drop is about 10 millivolts, which is less than 1% for the system they have been using. And then you measure the voltage drop across it. And if I measure the voltage drop across the resistor and I know the value of the resistance, then I know the current through that resistance. Basically, that is the methodology they have adopted. Now, another way of doing that is, doing such a measurement is to use certain other sensors. They are what are called current sensors Hall based on Hall effect, where again you can introduce the sensor in series instead of the 0 ohm resistor. The voltage drop will be very low, and then you can pick up the current value. So multiple different ways of doing this. And they have used a data acquisition system with 16-bit ADC and running at 250 kilo samples per second. Okay, so this is again important, the choice of your because that determines the resolution or the accuracy with which you can pick up the current values and hence the power values. And whether you are interested in dynamics, right? Are you interested in tracking the changes in current, or are you interested in tracking the average? That determines the sampling rate, right? If you are just interested in the average current, then you just put an ammeter. Ammeter is like giving you really the average current. But if you really want to know also the time profile of the changes in current, as you turn it on, current goes up, then comes down, etc., then you need a higher sampling rate, and the sampling rate will be determined by the Nyquist criteria, right, for the bandwidths you want to measure. So this was the experimental setup. So they set it up, they had a bunch of different benchmarks, they ran which stresses different things: video, audio, networking, computing, storage, etc. And then they collected the results and have presented that in this paper out here. So the first is the number of graphs. I won't go through all of them. You should read up this paper, and then we can again go through in a little bit more detail in the next class and discuss it some more. But basically, just a small preview of some of the results they have reported. One is in the suspend state, you still have there's about 70 milliwatts of power, and you have about 10 milliwatts with the 12 milliwatts with the CPU. Mainly again still your GSM modem is about 30 milliwatts, and then graphic is about 10 milliwatts, and the rest are 5 or less. So the radio and the CPU consume quite a bit of power. Here in the suspend state, presumably the display is off. You have the idle state where backlight is off, and this power is more, about 250 milliwatts or so, and now the graphics is consuming much more power. So these kinds of profiling is very important, because only then will you know how to optimize the power of your system, and you really need to get measurements done to see where is power going. Now the lighting, because in the phone you have the display, and then you have the backlight for the display. That backlight power really depends on the brightness level. If you keep it very bright, full brightness, you have about 400 milliwatts of power. That's quite a bit of power, and then you can get it down all the way to 0. So so there is a certain, it's not a linear type relationship. They have some kind of quadratic relationship out here. When you run these different benchmarks, so you see the CPU has ability to run at 2 different frequencies, 100 megahertz, 400 megahertz. So this is something which we will discuss later on in the course, because frequency is one tool which allows you to control the power dissipation. The rate of operation clearly determines the rate of energy consumption and hence power. So that is a way by which you can modulate the power consumption. And so typically modern systems now give you the ability to adjust the frequency of operation. So they have taken a number of different benchmarks. So what all this earthquake, VPR, GZIP, etc. are all programs from these benchmarks. These are all kind of well known if you do work in the processor design space. And then when you run it, you measure the power consumption, and you can see that the processor power is much more than the memory power. And the processor power, you see, it's 60 milliwatts to 180 milliwatts, between 100 to 400 megahertz. Example here it is 60 milliwatts to 160 milliwatts, and so on. So one thing is that you see that as my frequency, for example here, my frequency went from 100 megahertz to 400 megahertz. My power hasn't quadrupled. Frequency has quadrupled, power hasn't quadrupled. Okay. So what that tells me is that clearly some component, because as you all know, most of you have done the digital VLSI class, the dynamic power dissipation is proportional to frequency, CV square. Right? If power was completely dynamic power, then you would have expected the power to quadruple. But power is not quadrupling, which means there is some amount of power which is independent of frequency. And that is not that hard to believe, because you have static power, which is power due to leakage and so on. In addition, you see that depending on the application, the change in power is also different. Earthquake application going from 60 to 180, whereas VPR is going from 60 to 160. So application dependent dynamic power versus static power is also there. Right? Some application there is more dynamic power consumption, some application there is less dynamic power consumption. So so that is just one observation to keep in mind, and we'll kind of come back to this later in the course. Power for storage, right? So when you're trying to do, so here what they do is they have these benchmarks which are just doing reading and writing into the memories. And when you do that, what you find is that the power consumed by the storage devices themselves is less than the power consumed by the CPU, because there is CPU has to do some application, run something to go and write into the memory. So the storage power is not that bad, even to write into a SD card, which is kind of like equivalent to a hard disk. The power consumption is comparable or less than that for in this case of the CPU. And the power for reads and writes are not exactly the same, they are a little different out here. And that is also because of the nature of the way, it depends on how writes happen in these storage devices. Right? Sometimes for some of these storage devices you have to erase and then write and so on. So the steps involved and the energy involved is much more. Here what they have done is they have taken applications which basically do a lot of networking, right? Internet IP, essentially connect to some website, etc., etc. And when you use the Wi-Fi, so you have two different ways of connecting to the internet. You either use Wi-Fi or use your GPRS, and based on that, either you consume a lot of power for Wi-Fi, which is 700 milliwatts, or you consume power and when you do the Wi-Fi based application, the GSM power is very low, but it's not zero. Whereas when you do the GSM based application, mostly it is GSM, but the power in the Wi-Fi is less. So it's kind of interesting that the Wi-Fi and GSM power are a little different. The question, I don't know, we have to read the paper in more detail to see whether the throughputs are the same. So if they are the same, then it's saying GSM is a more efficient way to go to the internet, which is at least for this particular system. And you're completely dominated by the communication. You see the power for the CPU and memory is so small. And this is something which you will often find, is that in these devices which have connectedness, the power of the communication and the radio will completely dominate and overwhelm the total system power consumption.
Does the power consumption in case of GSM vary with the coverage area also?
The question is, will the power consumption of GSM vary with the coverage area? I don't see. If they have smart power control, etc., then it could vary, but I'm not sure whether that is kind of implemented in all. Throughput will vary, yes, but power consumption wise, I don't know the answer. My guess is it's not going to vary too much. But there's something, one can look up some of the data sheets of the GSM modules to see if they have provided us the smarts to adjust the power consumption of the GSM itself.
I think it might vary.
Pardon?
If it is far away from the tower, it should transmit at higher power level.
It should transmit, yes. So there will be some, the thing though is that the power consumption even for the GSM module has multiple components, right? And there is a power amplifier finally, of course, which is delivering the power, radiated power. And of course, if you increase the radiated power, the overall power consumption does go up. But how much of that is a fraction of the overall power? So it will be a large fraction, but is it completely dominated by that? No. processor power, here what they have done is they have also taken two standard commercial phones, Nexus and Moto G, and then they have looked at the power consumption for these different applications, and these processors, as I said, come with two different frequency settings. Firstly, the lower frequency and higher frequency, and for example, in this case, it's 200 megahertz and 900 megahertz, so quite a bit of difference in the frequencies, and correspondingly, there's quite a bit of difference in the power consumption. Whereas this other phone, there doesn't seem to be, I think it's a 2:1 change in frequency, but still there's not much change in power. So really depends on the kind of hardware these vendors are using as to how efficient the system is in terms of power consumption. So these kinds of studies are very important for a system designer, because then you get an idea as to how to optimize your system, how to write your software so that you take advantage of, for example, the frequency, capability of adjusting the frequency. And if you find that your battery is running low, you kind of shut off things, you run things slowly, etc., to try to prolong the life of the battery. So some key observations, of course, from this study was that in the case of this smartphone, a lot of power is basically static power, which has nothing to do with the kind of applications you're running, and it's just basically things like the GSM modem, the backlight, they dominate. And so the only way to deal with that is shut off those guys as much as possible, keep them off, keep them disconnected, right? And the other interesting thing, which of course we didn't have time to go through in this particular lecture, but we'll come back later, is that lower, when you run these lower frequency doesn't mean low energy, and also lower voltage doesn't mean low energy all the time. What happens is when they reduce the frequency, they also have the ability to reduce the voltage. Okay, so that not only reduces power, that also reduces the energy, reduces the energy. But the thing is that if I have a certain application, right, there's a certain program you want to run, like say the earthquake program, which has so many million instructions. Right? When I reduce the frequency, it just takes longer for the program to finish because it's running slower. During that portion, components which are dissipating static power, maybe your GSM modem is on, your backlight is on, they are going to consume more energy because you're keeping, for that application is taking more time to finish. For during that time, the static components are consuming more energy. So that is why time comes into the picture as far as optimizing energy goes. It's not necessarily true that running slower will also reduce energy. You could actually end up with consuming more energy, and hence there is this notion of a point of optimum energy. There is a point, the speed at which you have to run, which will minimize the overall energy consumption. And we'll kind of discuss that later in the course. Discuss that in more detail, how you can automatically try to track that point of minimum energy, etc. So what we'll do is that, this is just a snapshot. Now the thing is that, of course, in this course we will not be, what this paper does show is that yes, the backlight, GSM, etc. are very important, but if you also see the CPU power, that is also quite significant, right? Sometimes the CPU power can be, if you see, 900 milliwatt for certain applications and so on. So it is not insignificant. So the computing power is also quite a bit, and so this course will focus only on that computing power. There are other systems where we don't have the backlight, we don't have the GSM and so on. So clearly there the power will be dominated by the computing, right? A lot of the embedded platforms where maybe implants, smartwatches, etc. So the course will focus on basically on power reduction techniques for chips, and we'll look at power reduction techniques which are well known, maybe also some new techniques people are experimenting with, dynamic power techniques, with energy optimization techniques. Also look at low voltage, reducing the voltage is another very important way of reducing power and energy, and how to do, what are the considerations, what are the challenges in doing ultra low voltage design.